Alright guys, today we're talking about lesson 12-2, which is about chords and arcs. We're going to split this section into two different parts, so I'm not referring to part one of the video, it's just two different parts of the actual section because there's a lot of theorems to cover here. So we're going to cover two of the theorems today, each of which have their own little parts. So get ready to go. Let's start with some vocabulary. First of all, we know, or we're now learning, that a chord is defined as a segment whose endpoints are on a circle. A segment whose endpoints are on a circle. So for example, I'm going to draw a chord here. This blue segment that I just drew is a chord, so we would say that segment, let's call this point A and this point B. We would say that AB is a chord because it has endpoints A and B, both of which are on the circle, meaning on the orange line exactly. Okay, so that's what a chord is. I could ask you a couple questions like, is a diameter a chord? Well, if we draw a diameter, going through the center of the circle here, that's what a diameter is, it would go directly through. All that matters is that it has endpoints on the circle. So again, C and B are on the circle, therefore BC is a chord. Right? So any diameter that you draw will be a chord. Now, I could ask you, is a radius a chord? Well, if I start from the center here and connect to any part of the circle, then we would see, let's call this point D and this point E. Well, DE does not have its endpoints on the circle. One of the endpoints is, that's point E, but the other endpoint, D, is not on the circle, it's in the circle, so DE is not a chord. Okay, so that's kind of what we're referring to when we say a chord. AB, BC are both chords, but DE is not because its endpoints are not on a circle. So, what are we going to do with these chords? Well, there's a theorem, and if you copy this down, make sure you have, these different things kind of in a triangular, or you'll see how I piece it together, but kind of shaped like that on your paper if you're writing this down. But this theorem has three different parts, and it goes in a circle. So it says, within a circle, or within congruent circles, it doesn't matter which one. The first part says that congruent central angles have congruent chords. So this is part one. Part one says that if you're given this, if you're given that you have congruent central angles, then it implies that you also have congruent chords. Okay? Part two says that if you have congruent chords, then you have congruent arcs. So this is part two. If you have congruent chords, then you have congruent arcs. And then part three says, if you have congruent arcs, then you have congruent central angles. So you may see, like in your book or a workbook that you're using or something, it'll have it like part one, part two, part three. I think it's easier just to see that these are all connected to each other. If you're given congruent central angles, well, that implies congruent chords, which therefore implies congruent arcs, which then goes back around to implying congruent chords. So they're all connected in that way. We're going to prove part one here. So we're going to prove specifically this connection right now. So the proof of part one, it says that we're given that the central angle, again looking back here, we're proving that given the central angle here, given this, we want to prove that the chords are also congruent. So we're given that ACB, which is this angle here, is congruent to angle DCE, which is this angle here. I intentionally drew it where it's not vertical angles, but vertical angles can come up in this lesson. So, and we'll look at an example in a second where that does happen. But they don't have to be. They just have to be congruent central angles. again, where C is the center. We want to prove now that AB is congruent to DE. We're trying to prove that the chords formed by those central angles are congruent. Okay, so the chords formed by them are congruent. So here's the proof. Hopefully you notice, at least, let's do a quick outline. Hopefully you notice that we have a triangle here and a triangle here. And to prove that parts of triangles are congruent, it usually helps to prove that the triangles themselves are congruent, because then we can use good old-fashioned CP-C-T-C. So that's the plan. Okay, let's see if that works. So what do we know? We know, first of all, statement 1, if we're doing a statement and a reason, right? Statement 1 would be the given information. Angle ACB is congruent. It's congruent to angle DCE, and that's given to us, right? So that's given. What else do we know? Well, we know it's a central angle, right? That's the central angle they gave us, which means that each of these segments here are each a radius, so we can say that each of those segments is congruent. We can say that AC is congruent to BC, which is congruent to DC, which is congruent to EC, right? So AC is congruent to BC, it's congruent to DC, it's congruent to EC. I'm just combining this all into one statement, and that's because they are. So it's just definition of radius, right? Radius is congruent. So we know each of those is a radius. Well, if we know that that's true, then if we're looking at these two triangles, we can say that triangle ACB is congruent to triangle DCE. And hopefully you can see if this is congruent to this and this is congruent to this, then we have the included angle, right? The included angle here is congruent. Then we can use SAS to show that the two triangles are congruent. And once you know the two triangles are congruent, you can then say that AB is congruent to DE. And how do we know that? CPCTC. Corresponding parts of congruent triangles are congruent. Okay, so that's just kind of how the proof works. You can prove the other two parts in a similar fashion. I don't think it's really a good use of video time, but if you want to, kind of get the mechanics of that better, I highly encourage you to try parts 2 and 3 to see if you can come up with those proofs as well. But let's look at an example here. So it says in exercises 1 and 2, the circles are congruent. What can you conclude? Well, let's look at this first example. So we're given, the only thing we're really given here is that these two central angles are congruent, right? And when you know that the central angles are congruent, let's again go back here. You know the central angles are congruent, so we're given, again, we're starting here again. Given central angles are congruent, which means we can then say, right, follow this path, just follow it around. You can then say that the chords are congruent. So let's go back here. Central angles are congruent, therefore we know that BC, that's the chord formed by that central angle, is congruent to the chord formed by this central angle, which is YZ. Okay, then if we're following the circle around, well, now we know we have congruent chords, which means then we can say, well, we must have congruent arcs as well, right? So we can say that arc BC is congruent to arc YZ. So we can conclude both of those things. Again, that's just following the path around from your proof, right? It's just following it around. So if you want to go back to your picture, just follow it around. So look at example 2 here. We are given just that these two central angles here, angle TFE and angle MKL, are congruent. But we also see that TG is, or that's terribly traced, but TG is a diameter, EH is a diameter, which means we're going to form vertical angles here. So there's a lot that can be given here. So we know that First of all, just from what they give us, you should be able to say that TE is congruent to ML. But because, again, let me change colors here to kind of magnify this, because these are vertical angles, we can also say that these chords here are the same as the other chords we just signified, because again they have congruent central angles, right? So we can say then that this is congruent to HG and JN. So all of those chords are congruent because they all have the same central angle. We can then say the same thing about the arcs themselves. So we have arc TH. We have arc TH. We know that it's congruent to, oh, not TH. What am I talking about? TH is over here. I apologize. Which we can get to later. You could also conclude those things later, but for now, not super important. So let me back up here. Not TH. We have arc TE. It should be the same, basically the same thing that you had written up here, except now instead of putting the segment symbol, you're putting the arc symbol, right? So HG, which is congruent to JN. Okay, so that's kind of how that works. That's how we can conclude some things. Looking at the one given information, they can give you more from there. Anyway, another theorem. So within a circle, or congruent circles, we have another two-part theorem. So first of all, so we're going to start this direction here. If the chords are equidistant from the center, then the chords are congruent. So if we have, here's the center. Let's say I have a chord here and a chord here. Okay? If I know that they're equidistant from the center, which means, again, to measure distance, we have to meet at 90 degrees. So if I know that this length is congruent to this length here, then I can say that the chords themselves, these blue chords here, so this chord and this chord, are congruent to each other. Okay? I can also go backwards in this. I could say, if I know that the chords are congruent, then I can also say, so now it's flipped, if I know this is congruent to this, I can then say that they are both equidistant from the center. So it goes both directions. If you know they're equidistant from the center, then they must be congruent. If you know they're congruent, then they are equidistant from the center. So you should be able to write this as a biconditional statement, which I'll leave you to do later. That would be a good question to put on a quiz, for example. Just throwing it out there. Anyway, let's look at an example. So we want to solve for A here, right? So first of all, what do we know from the picture? We know, so I'm going to solve for A. We know that these two distances from the center to the chords are congruent because they're both 9, right? So we're given that the chords are equidistant, which means the chords must be congruent. So how long is PR? Well, this part here is 12.5, which means this part here is also 12.5. So PR is 25 units, right? And we also know that PR is congruent to, not congruent to, we can say that PR equals A. It's the same distance as A because the chords must be congruent, therefore A is also 25. So that's kind of the mechanics of how that works. Okay, that's just looking at mechanics itself. Yeah, beyond that, I recommend doing a couple problems in your book. This should be the only part for today's lesson. It's pretty straightforward. But if you're confused at all, try the proofs from the book. They're built in as exercises in your book, or just try them on your own if you don't want to use the exercise. And then, do a couple example problems and make sure you're comfortable with the mechanics. So, anyway, enjoy the rest of the weekend. Bye, guys.